Does it mention in my problem anywhere about mass or grams?
No.
No. So do I use molar mass anywhere?
No.
I will not, right? I'm only using molecules and moles. That's it. So I'm going to start my problem with what I know. 5.12 times 10 to the 23rd molecules. Does it even really matter what the formula for acetic acid is?
No.
If I don't have to have molar mass, then it really doesn't make a difference. Is it helpful if you know it? Sure. But is it going to make a problem? No, it's not going to matter. So we're just going to keep going. We're going to get rid of molecules and go to moles. All right. Once I'm at this step, what does moles always get?
1.
The 1. And what does all molecules always get? Avogadro's number, 6.022 times 10 to the 23rd. Did we store that in our calculator yesterday?
Yeah.
Okay. And did I show you how we abbreviate it? NA. If you don't want to write it every single time, you can write NA. Right? That'll tell me that I'm using Avogadro's number. Okay. I'm going to multiply it across the whole top, divide by the whole bottom. A small number, because I know it's going to be less than what? Less than 1. I'm starting with less molecules than Avogadro's number, so my answer, I think, should be less than 1. Okay? 5.12 times 10 to the 23rd divided by Avogadro's number gives me 0.85 moles of acetic acid, which is HC2H3O2. Okay, does that match our expectation? Okay, right, we were expecting to have a pretty small number here. 4.52 moles of cobalt contains how many molecules? Does it ask me about mass or grams? So I'm not going to use molar mass at all. 4.52 moles. What are we expecting here for our number? I don't think so. I'm looking for the number of molecules. It's going to be really big, like times 10 to the 20 something big. Okay? So moles to molecules. Okay, it would be nice if I know what cobalt sulfate is, but it's not the end of the world. 1 mole is equal to Avogadro's number. 4.52 times 10 to the 23rd. So 2.72 times 10 to the 24th molecules. Yeah. Relationship. I know the relationship between grams and moles, and I know the relationship between moles and molecules. And so moles is going to be my middleman for all my conversions. I'm going to go from grams to moles to molecules and back, right, if I need to go back. But I can't make any assumptions as to how many molecules are in 1 gram, how many grams are in 1 molecule, because in a T-chart, they have to be equivalent statements. One of these is equal to so many of these, so I have to use moles. Okay? So we're going to start with our a practice here. How many molecules are in 633.21 grams of barium permanganate? Okay, so let's see, what is it asking for? It's asking for molecules, which means we use what? What are we going to use to get to molecules? We're going to have to use Avogadro's number. And what would I use if I have grams? I'll need the molar mass. So I'm going to have both of them to help me solve this problem. It mentions both molecules and grams. I'm going to need them both. Okay? So let's start with what we know. 633.21 grams. Do I need to know the formula for barium permanganate? I do, because I'm going to need its molar mass. So now I've got to step to the side here and figure out what's the formula for barium permanganate. Okay? Permanganate is not one you memorized, but it ends in an 8. So where do you think I'll find it here?
In the box.
In the box, right? I'm going to look for it in the box. So barium is in group 2. Ba, and it's +2. And permanganate, MnO4, and its charge is -1. So how will those fit together? BaMnO4 2, right? With the parentheses, because I need 2 of those permanganates. Okay, now I'm going to again encourage you to keep the label in the T-chart. Some of us just do the T-chart with straight numbers. Number one, it's difficult for me to tell what's happening, but it's more difficult for you to tell what's happening if you get confused. So I'm going to go ahead and keep that in this chart, okay? Let alone the fact that eventually in this chapter, we're going to convert between multiple substances. So we have to make sure that we're staying organized. So grams of barium permanganate goes on the bottom. What can I go to? Can I go directly to molecules? Yes or no?
No.
I cannot. I have to go to moles. Okay, BaMnO4 2. Do you guys prefer to put the numbers in as you go, or do you like to do all the units? Okay, do you have a preference? Okay. It doesn't make a difference. It matters none, but we can keep going. If I've got moles here, I'm going to get rid of moles. BaMnO4 2. And I'm going to go with molecules because that's what I want to end up with. Okay, now I can look at putting my numbers in. I know moles is going to get the 1 in both scenarios because I can tell how many things are in 1 mole. I can't tell how many moles are in 1 gram. I can tell how many grams are in 1 mole. Okay, so here we'll need to go the molar mass.
So
Barium plus 2 manganese plus how many oxygens? Plus 8 oxygens.
Yeah, 56.
Okay, so molar mass here. Listen, I'm hearing some molar mass issues. So for barium permanganate, MnO4 2, barium is 137.3 plus 2 manganese. Okay. Plus how many oxygens? Now, 4 times 2 would be 8. Okay, does that make sense? Okay, I'm missing one part of my T-chart left. What has to go with molecules? Avogadro's number. Okay, so I'm still going to plug in 6.022, but I don't want to write it out every time. Okay, so now I can multiply across the whole top, divide by the whole bottom. 633.21 times Avogadro's number. I like to hit enter after the numerator. That's not the end of the world if you don't. 375.3 is on the bottom. I ended up with a value of 1.02 times 10 to the what? 24th. Good. 1.02 times 10 to the 24th. If you think that's a long problem, we are just getting started.
Yeah, that's what the last class was saying.
Yeah, you betcha. Okay? Tell me what questions do we have about putting those numbers in? We need to lead with our units, right? So grams cancels, moles cancels, right? We're going to lead with what our units. We have to know what our pathway is there. Okay,
Just to make sure.
All right, potassium hydroxide says how many grams are in this many molecules of potassium hydroxide? Grams. So I'm going to have to do a 3-part T-chart here. 6.244 times 10 to the 23rd molecules of potassium hydroxide. Do we know what it is? KOH. Okay, what's got to go on the bottom here? Molecules of KOH. Can I go directly to grams? I cannot. I have to go to moles of KOH. I'm going to get rid of moles of KOH and go to grams of KOH. Then I can go in and put in my numbers. I know moles gets the 1. I know molecules always gets Avogadro's number. And in the chart with grams always goes molar mass. I had around 56 for my molar mass for KOH. All right, what's our expectation here? A big number, small number, or a regular number?
Big number.
What'd you say? What's our expected answer here? Really big, really small, or somewhere in the middle?
Pardon me interrupting.
So we do Avogadro number.
Miss Noll, I caught that. You put a G down.
I did.
You erased it.
I did. I got about 364.4 grams of manganese.
For some reason, I keep getting like the decimal places off on my calculator.
Okay, the formula for rubidium phosphite, excuse me, I misspoke. Rubidium is Rb and it has a charge of +1. Phosphite, what do we know about phosphite? One less oxygen, so PO3 minus 3. So how is that going to fit together to form a compound? Good. Rb3, PO3. Can I reduce those?
No.
I cannot. Right? This 3 is part of phosphite's identity, and so it's non-negotiable. Right? There's a 1 out here, but we'll leave that off if it's a 1. Okay? So I want to answer some questions about rubidium phosphite first. Okay? Before we even get into the math, I want to answer some questions about this. Okay? So you don't have to write this down. I just want you to sit and I want you to think. Okay? If I have 1 rubidium phosphite molecule, how many rubidium atoms do I have? If I have 1 molecule of rubidium phosphite, how many atoms of just rubidium do I have? 3, right? Because it says right here, 3. How many oxygen atoms do I have? 3. Okay, if I have 2 rubidium phosphite molecules, how many oxygen atoms do I have? 6. If I had 10 molecules of rubidium phosphate, how many oxygen atoms do I have? 30, right? Do we see how that scale works? Okay, so now answer this question. If I have 1 mole of Rb3PO3, how many moles of just oxygen do I have? 3, right? The ratio remains the same. I have 3 oxygen atoms per molecule. So if there is a whole mole of these molecules, that must mean that there are 3 moles of oxygen atoms. Okay? If we have a mole of this compound, 6.022 times 10 to the 23rd of these molecules floating around, and they all magically separated, I would have 3 moles of oxygen atoms, 1 mole of phosphorus atoms, and 3 moles of rubidium atoms. Do we see how that works? Yes or no? I need a confirmation on that. Okay? That ratio remains intact, and that's a big part of what we're doing here in this problem. Okay? So let's go ahead and just start breaking down the problem now. We're going to have to switch between examining the total compound to examining just oxygen. Okay? For these questions, there are multiple ways to get to our final answer. I'm going to show you what I think is the quickest, okay? But there are lots of different ways you could walk through the problem involving percent composition and involving a T-chart. So you can do lots of different ways, but let's try this first one, okay? I'm going to start with what I know. I'm starting with 4.55 times 10 to the 23rd molecules of rubidium phosphite. So 4.55 times 10 to the 23rd molecules of Rb3PO3. Okay. I eventually want to get to a place where I have the mass of oxygen. So I'm trying to get to grams of just oxygen, right? That's where I'm trying to go here. Grams of only oxygen. So I'm going to have to add one step to my chart. And I'm going to show you when that comes into play, okay? I've got to get rid of molecules because I can't ever compare things in molecules, right? Rubidium phosphite. And I'm going to go to moles of my total compound, Rb3PO3. Okay, let's go ahead and put in our numbers as we go for this one. For 1 mole of rubidium phosphite, there are 6.022 times 10 to the 23rd molecules of rubidium phosphite. Okay. Now I want to keep going. I've got to lead with my units, so automatically I know moles of Rb3PO3 has to go to the bottom. I want to get to grams of oxygen, but I cannot compare. I can't make a switch in any other unit besides moles. And so this step right here is called the ratio step. And it's where we examine the ratio of moles of my total compound to moles of just oxygen. Okay, this is where we did that comparison. And we say, if I have 1 mole of my compound, then I have 3 moles of oxygen. Okay, so this ratio step, number 1, has to be measured in moles. That's the only time that I can have 2 different compounds in the T-chart. Okay, as if it's moles and moles. Okay, that's when I switch my comparison to looking at the whole compound to now I'm just looking at oxygen. And then I'm going to keep going and get rid of moles of oxygen and end up with grams of oxygen. Okay, so I added one step in there where I stopped looking at the total compound and I started looking at just oxygen. That's called the mole ratio step. So it has to be mole and mole. Okay, so let's put in our numbers here. We go back to examining regular 1 mole molar mass. Okay, so anytime we're between moles and grams, moles gets the 1. The mole ratio step is the only place where we could see the moles not get a 1. Okay, yeah, Owen.
Grams equals molar mass.
That's right, always. Okay, so let's multiply across the whole top and divide by the whole bottom. I'm actually going to change this question because I want to practice that other method. I want to say how many grams of carbon atoms? How many grams of carbon atoms are found in this mass sample of copper 1 carbonate? Okay, so I'm still going to look for grams of pure carbon. Copper 1 carbonate. Okay, so copper plus 1 carbonate is CO3 minus 2. Right? Remember why can you see now why I thought it was so important for you to memorize polyatomic ions? Look how much time it saves me if we know those, right? Yes, they're in the box, but if you know them, it saves you a lot of time, okay? So now we're going to go Cu2, CO3. Okay? Now, I'm going to show you the percent composition pathway to get to our answer here. The percent composition method works well when both of our things are grams. When we're looking at grams of both, we can use percent composition a little quicker than maybe we could do the T-chart. Okay? The T-chart would still work. It would work fine. It always works. But this might be a little simpler. So I'm going to let you kind of choose how you get to your final answer. You can choose which method works for you, okay? But essentially, what we can look at here is to find out, well, what is the percent of carbon in that compound? And then I can just say, okay, if it's 20% carbon, which it's not, but if it's 20% carbon, then what's 20% of that number, right? What's 20% of my sample? Because I know that that is pure carbon. So we're going to work it that way, okay? So let's go ahead and find the percent of carbon in this compound, okay? Do you remember how to find percent composition? Yep, we need to find the whole mass first. So the molar mass of copper carbonate, let's find the molar mass of that. I got about 187. I don't know if that's what you had or no. Okay, 187. So if I want to find carbon's percent of that, I'm going to take carbon's part, which happens to be just one carbon, so 12, divided by my total, right? I'm going to take the part divided by the whole. And I'm actually going to, it gives me 0.064, so that would give me about 6.4% carbon, right? Would we agree with that? My compound is 6.4% by mass that is pure carbon. Would we agree? So now, if I know my compound is 6.4% carbon, I just need to go answer the question, well, what is 6.4% of 551.29? Okay, and to do that, all I have to do is take that decimal, 0.064, and take it times my total. And so that gives me 35.4 grams of carbon in my sample. What if my answer had come out to tell me that my carbon sample was 600 grams? Would that have been a problem?
Yeah.
Why would that have been a problem? That's right. It would have been greater than the sample I even have. There's no way I could have had 600 grams of carbon out of a 551 gram sample, right? So we need to make sure we have a range of expected answers here. I'm going to show you how either method would work. So you don't need to have to write down what I'm doing next, but I'm going to show you how you could also do a T-chart with this method and it would have worked the same way, okay? So I'm just going to bring this down here. And if I start with 551.29 grams of Cu2CO3, grams of Cu2CO3 to moles of my total compound, moles of my compound to moles of just carbon, moles of carbon to grams of carbon. Okay, and so if I put in my numbers, 1 to 187, what's my ratio here between the total and the part? If I have 1 mole of my of my compound, how many moles of carbon do I have? No. Just 1, right? If I have 1, I only have 1 carbon atom. So 1 to 12. So 551 0.29 times 12 divided by 187 gives me 35.4 grams of carbon, right? So I get the same answer either method I go about it. Okay? Typically, if you have any dealing with Avogadro's number, the T-chart will be better. And if it's grams and grams, the percent composition method might be quicker. But I'll leave that up to you. I don't care which method you use. Both work perfectly fine. So you could decide.